Good morning. Now I am going to discuss about the different types of transistors, that is resistive, inductive and capacitive transducer. Coming to the first one, that is the resistive transducer. So it's a resistive transducer is also called as a resistive potentiometer or pot. So this consists of a resistance element provided with a sliding contact. So potentiometer, we all know that. So a potentiometer will be having a sliding contact. That sliding contact is also called as a wiper. The motion of this sliding contact may be translatory or rotational. So this can be moved straight or rotational. So some of the resistive potentiometers will be having both translatory and rotational. So the combination of both is nothing but called as a helix. These are called helipots. General translatory or rotational are called as pots, whereas the helical resistive elements are called helipots. This is the translatory motion, this is the rotational motion, and this is the helical motion. So here all these type of resistive transducers require input supply. So these transducers are called passive transducers. Okay, so this is the input supply which we are giving to the two terminals of this resistance, and this is the variable terminal, that is the sliding contact. So this sliding contact is called the wiper, which moves either up or down, and between these two terminals you can get the output voltage. So the motion of this wiper is in the translatory motion. So this is called translational resistive potentiometer. This is the next one is the rotational resistive transducer. That means here the wiper will be moving rotationally. So this is called rotational transducer. Here the wiper will be moving both the translational and as well as the rotational, so it is called the helical transducer. In all these three we can observe we need an input supply given to the both the ends of the resistance. So and at the other terminal, that is wiper and the neutral, you are getting the output voltage. Wiper and the neutral, you are getting the output voltage. And based on the position of the wiper, you will be getting the output voltage. So that means based on the length of the resistance used, that it is proportional to the output voltage. So we can say that V out by V in is equal to the output length by, that means this length divided by total length. So we can consider this as the ratio of output voltage to input voltage, which is proportional to the length of the resistance used. So this is about the resistance transducers. All these require input voltage, so these are called passive transducers. So as we have discussed, translatory resistive elements are linear, that means straight devices, whereas rotational resistive devices are circular. The wiper moves in the circular direction, and these are used for the measurement of angular displacement. So these are used for straight displacement, whereas here angular displacement. While helical resistive elements are multi-turn rotational devices. So it consists of multiple turns. So in which these are used for the measurement of either translatory or rotational motion. So here, as we have discussed, a potentiometer is a passive transducer since it requires an external power source for its operation. Next one is the inductive transducers. So inductive transducers means here we are based on the physical motion is going to convert into inductance. Inductance is modified so that we can get the motion. So here this is definition of the inductive transducer is an inductive transducer is an electrical device used to convert physical motion into modified within inductance. So physical motion, you can convert this motion by converting the inductance. so that you can measure the physical motion. So how can you measure this inductive? How can you measure this inductance? So this inductive transducer is going to work on three principles. Those are self-inductance change, either mutual inductance change or eddy current production. Coming to the first one, self-inductance change. Self-inductance means L. So the formula for self-inductance L is equal to N square by R, where N is the number of turns and R is the reluctance of the magnetic circuit. Reluctance of the magnetic circuit. So we know that reluctance, again, what is reluctance? R is equal to L by mu into A. That is permeability of the circuit, permeability of the coil, area of cross section and length of the coil. So if you substitute this R value in this inductance, you can get L is equal to N square mu A by L. So that means you can measure the self-inductance by measuring the by varying the number of turns of the coil, or by varying the permeability of the coil, area of cross section or length of the coil. So in these ways you can, if you vary any of these three, or you can vary the self-inductance. As you vary the self-inductance, you can vary the motion. So in that way you can measure the motion of the motion of the circuit, physical motion. Coming to the second one, we have discussed that there are three methods, three working principles. Those are self-inductance, mutual inductance change, eddy current change. So as of now, we have discussed about self-inductance change. Coming to the next one, that is mutual inductance change. So what is the formula for mutual inductance? Means M is equal to K into square root of L1 L2. Here K indicates the coefficient of coupling and L1 L2 are the two coils. Two coils. So the L1 is the coil inductance of self-inductance of first coil and L2 is the self-inductance of the second coil. So if you vary anyone L1, L2 or coefficient of coupling, you can measure the mutual inductance. So this can be explained by using this diagram. See here, the coil is wound over the core. So on these two coils are being wounded. One is the primary coil L1 and other one is the secondary coil, that is L2. So both these coils are wound on this core. So it consists of two self-inductances L1 and L2. So this is the core. On this one, induct coils are wound. For these coils, you are giving some supply. So from this core, you are placing an iron piece here. So this is the iron piece which is placed nearby the core. And the distance between this core and the iron, there is some amount of flux passing from the core and the iron. So because of that flux, inductance will be induced. So that means mutual inductance will be there here. So here this forms the air gap here. This is the air gap which is between the core and the iron. So when you are moving this iron piece upward and downward, so in this direction and in this direction, that means if you move the iron piece near to the core, that means more amount of flux lines are changing. So that means the mutual inductance will be more. If you move the armature in the opposite direction, then inductance will be varied. So that means inductance will be reduced. So likewise, by varying the motion of this iron piece, that means the distance between the iron piece and the core is directly proportional to the mutual inductance. So from the mutual inductance, you can measure the physical motion. And the third one, we have discussed that there are three methods. Those are self-inductance change, mutual inductance change, and the third one is eddy current production. So first one, self-inductance change, we have studied. Mutual inductance change, we have studied. And the final one is eddy current production. So this eddy current production can be explained by using a conducting plate. So likewise, in the previous diagram as we have considered here you have considered this as the iron piece. Now you are considering this iron piece is between two coils now. So in this side there is one coil and in this side there is another pole. So between these poles you are placing the iron. So this iron piece can be moved downwards or left or right. So that means, so because of that, circulating currents will be formed on that plate. So we know that circulating currents mean eddy currents. So because of that, by changing the eddy currents, we can change the inductance so that you can obtain the physical movement. So these are the different types of inductive transducers. And next one is the capacitive transducer. So here you will be measuring the physical motion by calculating the capacitance. Okay, so for that you are considering this is the capacitive transducer. So here you are not giving any supply. So these are called normal transducers. These are called active transducers because there is no supply here. Self-generating transducers also you can call this. Okay, so here this is the complete insulating material. This is the complete vessel where you are considering. So in this vessel you can observe this is one plate. Initially this is the deflected diode. So this is not the one which you have considered. So this is the one undeflected diaphragm which you are considering, and this is one plate. So this is one plate and this is one plate. So what is the meaning of capacitance? Capacitance will be formed when two plates are separated by a dielectric medium, right? So that means you need to consider two plates which are separated by some dielectric medium. So this static plate is one plate, that means it is fixed inside this vessel. And the other one is this is the variable plate. Initially this plate will be vertically. But when you are applying some force or pressure on this undeflected diaphragm, what happens is this undeflected diaphragm will be deflected like this. It would be deflected like this. Now the distance between these two plates has been decreased. Distance between these two plates has been decreased. We know that C is equal to epsilon A by D. So as the distance is decreased, that means the capacitance will be increased. So as the capacitance is increased, and if you consider this in any bridge, if you connect this vessel in any bridge, example Wheatstone bridge or an oscillator circuit, then what happens is you can measure this capacitance. What is the amount of capacitance here? So by measuring this capacitance, you can measure the applied force. So we can, capacitive transducer means the transducers which measure the applied force in terms of capacitance. So capacitance can be measured by using the bridges or any oscillator circuits. So that by measuring that capacitance, you can measure the force applied on this transducer. Okay, this is about the capacitive transducer, and coming to the advantages of this capacitive transducers are. So the advantages of this capacitive transducers are it produces an accurate frequency response to both static and dynamic measurements. So these are for both the static as well as dynamic measurements. You can measure this frequency very accurately. And coming to the disadvantages, an increase or decrease in temperature to a high level will change the accuracy of the device. Will change the accuracy of the device. And as the lead is lengthy, it can cause errors or distortion in signals. So these are some of the disadvantages of capacitive transducers. So we have discussed about the resistive transducers, inductive transducers, and capacitive transducers. In the next class, we can discuss about the LVDT. That is also one type of inductive transducer. Those are linear variable displacement transducer. So that can be studied in the next class.